This. 1, 2, 3. No. 1, 2, 3. 1, 2, 3.
안 들려? 잘 들리는 것 같은데.
1, 2. It's working. But I think it's as a little bit delay. Yeah, but that's fine. I think for the questions, that's fine. Yeah, it's good.
Are you ready?
Yeah.
Good afternoon, everyone. I'm Roshan Dathathri from Microsoft Research. I welcome you to the session on optimizing ML communication. We have 4 exciting papers lined up, and I'll first invite Heehoon Kim to present his work on TCCL. Heehoon? Yeah.
Okay. Hello, everyone. I'm Heehoon Kim from Seoul National University. Today, I will introduce TCCL, pronounced as TCCL, our collective communication library for GPUs. This work has been done in Junyeol and advised by Professor Jaejin Lee. Nowadays, the number of parameters in the state-of-the-art deep learning models has grown to billions and even trillions. So training them in a single GPU is infeasible. The common practice to train such large models is to leverage parallelism. With parallelism, we can distribute computation across GPUs, or we can decrease the memory requirement for each GPU. However, parallel training introduces corrective communication, such as or reduce and or gather. Thus, the performance of GPU communication has become critical to training throughput. As a response, GPU vendors and researchers made libraries that provide efficient implementation of collective communication primitives. The most popular algorithm for primitives is the ring algorithm, and some previous studies synthesize new algorithms instead of predefined ones. The figure in the right side describes an example of ring algorithm for OR gather. Here, 4 GPUs form a logical ring, and each GPU only has a quarter of data. In each step, each GPU sends one of the blocks to the next GPU, like this, until all GPUs have all blocks of data. We should note that all transfers between adjacent GPUs happen simultaneously. We observe 2 types of GPU systems are used to train deep learning models. The first type is one we call a high bandwidth system, which is the whole off-the-shelf system produced by GPU vendors or partners. The representative example is the DGX from NVIDIA. So these systems usually have a proprietary high-speed interconnect, such as NVLink. We observe that existing libraries indeed achieve expected performance, because if we form a ring through the dedicated links, like in the figure, they support simultaneous transfers at a near maximum rate. The other type of system is one we call PCI-dependent systems. Small-scale academic institutions and startups, including our research group, rely on cost-efficient systems built by assembling server components and GPUs. So these systems lack dedicated links, so GPUs and network cards must communicate through PCI host bridge of the CPU. In these systems, the communication path in the ring algorithm will look like this. So in theory, the ring algorithm should still achieve the bandwidth of PCI links. However, we observe that existing libraries do not achieve the expected performance in reality. We identified that the root causes of performance degradation are related to NUMA architecture. So in NUMA architecture, PCI devices as well as memory channels belong to one of the NUMA nodes, as shown in the figure on the right side. We observe that transfers can slow down when simultaneous transfers go through the CPU in a specific pattern. There are lots of such patterns, and here we describe one of the examples. So here, the red arrow represents the transfer that GPU reaches the CPU memory in the same NUMA node. And the blue arrow represents the transfer that GPU writes to the memory of a GPU across the NUMA boundary. So each transfer alone achieves reasonable performance in PCI generation 3 links, which is around 10 gigabytes per second. However, when both transfers are executed simultaneously, they achieve unexpectedly low performance of 4 gigabytes, significantly lower than PCI link. Another reason is from poor placement of the bounce buffers. So in PCI-dependent systems, GPUs may communicate via a bounce buffer in the CPU's memory. For example, when the GPUs does not support direct access to their memory. If many bounce buffers are concentrated on the CPU memory in the same NUMA node, the bandwidth of the memory channel becomes the performance bottleneck. These congestions appear only when the multiple transfers are executed. So as previous approaches find the ring based on only the bandwidth of individual links, they are not identified or avoided by the previous libraries. So to this end, we present TCCL, a collective communication library for the ring algorithm specialized in PCI-dependent systems. Here, TCCL consists of 3 main components: profiler, pathfinder, and runtime. The profiler and pathfinder are used to find the best path, and the runtime executes the actual collective communication using the result found by pathfinder. We will look at each component in detail now. As we see earlier, the performance of the ring algorithm relies on the time for all simultaneous transfers to finish. However, we found that no existing benchmarks measure such time correctly because of initialization with a non-deterministic latency and overhead of spawning processes. Thus, we implemented a new multiprocess profiler specialized in the measurement of the time for multiple transfers to finish. TCCL profiler properly synchronizes and aligns the start of the transfers, and it also maintains a process flow with all underlying libraries initialized. TCCL pathfinder is the main component that automatically finds performant communication paths. So the key idea here is that it takes brute force approach. So it enumerates all possible communication paths and always profiles each path to avoid taking paths of low performance. But however, communication paths are determined by many factors, such as the order of GPUs in a ring and whether to use bounce buffer and NUMA node where the bounce buffers are placed. So simply trying all paths is infeasible. Thus, the pathfinder handles intranode paths and internode paths differently. The pathfinder first starts with the intranode pathfinding, which finds the best ring that visits GPUs inside the node in a similar way to Dijkstra's algorithm. As shown in the figure, the algorithm maintains a priority queue that includes sets of transfers and their profiled bandwidth. And in each iteration, like Dijkstra algorithm, the pathfinder picks the current best set and appends new transfers to explore more paths. And then these transfer sets are profiled and inserted back into the queue. Eventually, the algorithm will terminate when we find the best set is also a ring. The pathfinder stores the best ring for each subset of GPUs in a node to support the cases where only a subset of GPUs participates in communication. The pathfinder also maintains a cache to prevent a transfer set from being profiled twice. The caching greatly reduces the number of requests to the profiler by more than 90%. For internode paths, instead of profiling every path, we find the best ring by merging short linear chains, like in the figure below. First, it stores the best linear chain and its bandwidth inside the node with the same Dijkstra algorithm for intranode pathfinding. Then we find multi-node linear chains with the best bandwidth using dynamic programming. Here, with the assumption that there is no congestion in internode network, the bandwidth of new linear chains is estimated to be the minimum of 2 original bandwidths. As a final step, the best ring can be found among the linear chain where its first transfer and last transfer are the same, so that they can be joined to form a ring. We implement TCCL runtime, ticker runtime on top of nickel runtime. We reviewed GPU kernels of ring algorithm and corresponding host implementations, but ticker runtime modifies the ring's path to the best ring found by the pathfinder. Because ticker has the same interface with nickel, no code modification is required in usual applications such as PyTorch. We evaluate ticker in 3 different clusters. The first cluster is equipped with AMD CPU and 4 NVIDIA Tesla GPUs. The second cluster is instead equipped with 4 GeForce GPUs for evaluation with GPUs that do not support direct transfer between GPUs. The last cluster is equipped with Intel CPU for evaluation with CPU from a different vendor. We compare ticker with nickel and MCQ, which are currently the state-of-the-art collective communication library for NVIDIA GPUs. Here, we first evaluate ticker in 5 collective communication primitives that nickel supports. So on the first cluster, ticker outperforms baselines in configurations with 2 or 4 GPUs per node, while nickel and MCQ suffer from congestion between CPU memory accesses and GPU direct transfers. Ticker correctly avoids such paths. On the second cluster, ticker outperforms baselines in configurations with 1 or 2 GPUs per node. As GPUs in this cluster does not support direct transfer, speedup mostly comes from the better placement of bounce buffers. We saw similar trend in the third cluster, so we skip this now. We also evaluate ticker with deep learning training. We evaluated with various degree of tensor parallelism, where degree of 1 denotes the pure data parallelism. The speedup here depends on the types of primitives used in each configuration. Data parallelism utilizes or reduce, so ticker achieves 5 to 10% speedup. In tensor parallelism setup, or gather and reduce scatter was the main primitives used. So in contrast to data parallelism, the cluster with GeForce GPUs achieves higher speedup than other clusters. We recorded the time spent for finding paths in MCQ and ticker. So with the high cache hit ratio, ticker was able to find the performance path under 8 hours in the worst case. We think that a few hours of path finding is not a big downside, as it needs to be executed only once when the system is built. So as a conclusion, ticker is a high-performance collective communication library specialized in PCIe GPU clusters. So it provides automatic search for the best communication path and presents a new Dijkstra-like search algorithm and dynamic programming algorithm to reduce search time. As a future work, we want to extend ticker to algorithms other than the ring and also want to support author primitive. Ticker is open source at the following URL, so you can take a look at it. Thanks for listening.
Thank you, Heehoon. Any questions? We also have an online audience, so if you want to ask questions, just unmute yourself and ask the question. Okay.
Hi, Matt Sinclair, Wisconsin. Very interesting talk. I guess, can you comment a little bit about, the discussion about extending to things beyond rings? It seems like your algorithm is very tightly coupled to how rings work. And so I'm curious, how easy or hard is that going to be to use other primitives?
So for example, you mean author primitive? Yes. Yeah, right. I think it's not that easy. It's an open question for the research. But here in the Dijkstra-like search algorithm, we can append the arbitrary transfer to the current transfer set. So there is actually no limitation that it should be limited to the ring-like path. So maybe we can just change the routine that picks the new possible path. Then we can maybe easily extend it to the other primitives, I think.
Any other questions? I can ask a question. So So your profiler determines which paths take which time, right? So how closely related is it to the bandwidth in the spec of those links?
Okay, so in the ring algorithm, there is multiple steps, but in every step, each GPU sends the data to the next GPU, right? So they are simultaneously sending the data to the next next GPU. So our profiler basically measures the latency that one step finishes. So it is directly related to the actual collective communication performance when we are using the ring algorithm.
Okay, thank you. We can have the next speaker. So the next talk is Centauri. It's one of the best papers in ASPLOS. So it will be presented by Xingchao Zhu, and there's also an online presenter, Chang Chen. Please welcome the speakers.
Hello, everyone. The title of the paper that I'm presenting today is Centauri, enabling efficient scheduling for communication, computation, or live in large model training tasks with communication partitioning. And regrettably, the first author could not be here due to some issues. So my name is Qianchao from Peking University. The simultaneous execution of communication and computation represents a higher degree of concurrency. However, efficiently utilize this level of concurrency poses a challenge. For instance, direct scheduling cannot take full advantage of all resources. Yeah, resulting a significant idle gap. On the other hand, fine-grained kernel fusion also leads to substantial overhead. And our work, Centauri, offer a solution for scheduling with proper communication partitioning and achieve better resource utilization. The first challenge we faced was how to systematically exploring the overlapping space. And our insight is that communication inherently is a mapping transformation, also primitive of workload across a group of devices. Thus, a primitive group and workload naturally form the basis of the overlapping space. However, existing research in this table focus only on a subset of these dimensions. The second challenge is how to efficiently schedule the partitioned task. Our insight here is that the training tasks have the nature of a hierarchical structure, and we abstracted 3 dimensions from the training task, which are operation, layer, and model. Okay. Considering the aspects discussed above, we propose Centauri. And this figure shows its overall framework, which include 2 parts, communication partitioning and hierarchical scheduling. And communication partitioning consists of 3 sequential steps, include preteam partitioning, group partitioning, and workload partitioning. And on the other hand, hierarchical scheduling operates on 3 dimensions, include operation, layer, and model. Okay, let's first take a look at the preteam partitioning. A typical collective communication operation is reduced, which can be split into equivalent 2 collective operations, reduce, scatter, and all-gather, showing in this figure. Yeah, and the reduce scatter operation can be further divided into the reduce and scatter communication. And in this table, we have summarized the partition and corresponding scalability of some key communication primitives. Our takeaway is that the performance scalability is essential in primitive substitution, especially under the topology of heterogeneous bandwidth. Yeah. So therefore, primitive partition provide us with a finer granularity for overlapping. And regarding group partitioning, different network topologies of clusters may have different characteristics. Hence, I would convey that high dimension topology awareness is essential in group partitioning. This is predominantly due to the inconsistent communication overheads between internode and intranode. Yeah. So here we use the all-gather primitive as an example, and providing 4 different group partitioning methods across 2 nodes of 8 GPUs. Figure 2 first divides the original group into 4 subgroups. Then node 0 and 4 performed all-gather. Now nodes 1 and 5, 2 and 6, 3 and 7 do the same. Okay, then we divide the original group into 2 subgroups, which are all within the node and perform all-gather. Yeah, in this way, we can achieve equivalent operation. Yeah, and the methods of partition for figure 3 and 4 are also similar, but with different subgroup and granularity. The final partition is workload partitioning. First, we need to pick up a chain of dependent operations. Then we divide the dimension of operations into 3 types. Contraction dimensions, CD, like the second dimension of the metmor, and the non-split dimensions, such as the second dimension of the softmax, and the other dimensions. Yeah. At the same time, we must ensure compatible partition dimensions within the chain. Yeah. So after partitioning, yeah, another key question is how to scheduling. Yeah. First, we perform scheduling as per operation level. And our takeaway here is that logical granularity is better. Therefore, as shown in figure B, we introduce workload partition to more effectively pipeline communication and computation, and therefore eliminates the bubbles. And our second takeaway is to control the workload on the low bandwidth group. Yeah. And inefficient method is shown in the figure C, and we just introduce this in group partition. Because this scheduling resulting much more internal communication volume. And a more efficient way is to adjust the group partition and order, ensure that internode communication happens before intranode communication. Yeah, this configuration will result in a smaller idle gap. And moreover, we can make use of a more refined group partition and adopt interleaved intra and internode communication scheduling. In the figure E, in the figure E, we divide the original all-gather operation into 3 all-gather operations, and both C1 and C3 are performed intranodes, but C2 in the internals. Yeah. Then by adopting this fine-grained scheduling, we can eliminate more bubbles and achieve better overlapping. And the layer level scheduling mainly occurs during the backward phase. It involves 2 types of computation, updates to the activation gradients and the width gradients. Hence, this forming 2 critical passes. And in the implementation of Megatron, since the activation gradient is scheduled ahead of the width gradient, causing the overlapping performance of activation communication in sequence parallelism is suboptimal. However, Centauri maximize the overlapping through the dynamic scheduling, as showing the figure C. We first update the width gradients and followed by the activation gradients. This dynamic scheduling exhibits a better overlapping space. And the final scheduling level is the model. Firstly, we consider the model timeline under the pipeline and data hybrid paradigm. If we use the deep first scheduling, we can move the or reduce operation of this yellow stage forward. And however, only 4 chunks are not enough for fully overlapping. And but if we use the breadth first strategy, that is with a large macro band size, such as 16, although it can overlap more communication, it also need unnecessary memory consumption. Okay, therefore, through the primitive partitioning and the scheduling, we propose a method that minimize actuation memory yet maximize overlapping as shown here. Okay. For our evaluation setting, we employ 4 different sizes of llama and apply in different parallel methods. Moreover, we conduct the test on 2 clusters, named A and B. The configuration within the node are the same with A100 NV GPU, but there's a big difference in internode bandwidth. Then the baseline we combined, the baselines we compiled include Megatron LM with 0 optimization, PyTorch DDP, and OOO backpropagation. Under the single paradigm, we compiled it with fully sharded data paradigm, FSDP with 0.3 on cluster A. The group size was set to 16. The x-axis represented the bench size and the y-axis represented the model flops. The results indicated that large band size lead to better overlapping with a speed up of over 1.50 times. And furthermore, in data parallelism task, we can also achieve a maximum speed up of 1.35. Okay. And on the other hand, we also take a test for hybrid parallelism. We compare it with FSBP and FSDP plus DP and the TP plus PP plus DP take in Megatron. The total group size was set to 48 here, and you can see that our overlapping can also bring about the best acceleration effect. Finally, we also test the scalability separately on cluster A and B, and under the FSDP and combined task of FSDP plus DP, we both achieve a good scalability. And you can see when DP is employed with multi-stream communication, and all cases suffers from a performance drop. Yeah. In general, our acceleration effects is more noticeable on cluster A, where the bandwidth between nodes is lower than cluster B. Okay, thank you. Welcome. Welcome. Any question?
Thank you, Qianchao. Any questions?
Thank you for your great talk. I'm Ho-chan from UT Austin. So I was just curious if you assume some specific task graph, because if the dependencies are high and there's few opportunity to overlap the communication and computation, then I'm not sure if it is useful. I mean, I was just trying to understand. Yeah.
Okay.
Yeah.
You mean the granularity to find the granularity maybe cause the performance drop?
No, I just try to understand what is your assumption for the task graph that you're targeting.
Okay.
So dependency or all kind of things.
Dependency is our training task is sorry. Chen.
Gonna answer the question.
You mean the chain of the dependent operations?
Second,
Yeah.
wanna answer the question, you can unmute himself in the Zoom and then you can answer the question.
Oh, okay, okay. Yeah. Makes sense.
Yeah.
So I was wondering if that is better case your workflow, some kind of insight that or target or something.
Okay.
So if Chang, if you can unmute and answer as well if you want. Yeah.
Okay. The Charlie Chen is in the
Yeah,
remote.
yeah.
She can.
Yeah. I think in the interest of time, we can take it offline. Yes, Suchita, can you set up your laptop in my?
She's not on.
Yeah.
Okay.
It's fine. Thanks.
Okay.
Shina.
Okay.
So the next talk is from Suchita on T3. Yeah, Suchita Pati.
Good morning, everyone. I'm Suchita Pati. I'm a final year PhD student at UW-Madison, and I'm also part of AIMD Research. I'm here today to present our work on T3, a transparent tracking and triggering mechanism for fine-grained overlap of compute and collective operations on GPUs. So as all of you already know, this transformer models have scaled by several orders of magnitude, going from millions to trillions in just 5 years. And this has made employing multiple GPUs in a distributed setup a standard practice to execute them. Now, it's intuitive that these GPUs communicate with each other in a distributed setup. However, this communication cost is often exposed and can account for a large proportion of the execution time. And while fusing the compute and communication to overlap them in a fine-grained manner it can help, it is challenging to realize. And it requires an interdependent evolution of these compute and communication kernels. And additionally, like with any other overlap in hardware, it suffers from resource difference. We propose T3, which overcomes these challenges. T3 uses a hardware track and trigger mechanism to automatically trigger communication when the data is ready, requiring no change to the actual gem kernels. And furthermore, it leverages DMA engines and compute-enhanced memories to manage the resulting interference from overlapped communication and computations. So with that overview, here's a very brief outline of the talk. First, let's look at why this communication is a challenge. So here we show tensor parallelism, one of the key distributed techniques with inherent serialization of communication. Tensor parallelism slices a model layer across multiple GPUs, and then the resulting matrix multiplication of both the sliced layer activations and weights result only in partial outputs on every device. And this requires the GPUs to communicate these partial values and reduce them to get the final output before the next layer can execute. And in GPUs today, these gems, these sliced gems and all reduce are actually executed as serialized kernels. To quantify how much time we spend on these all reduced kernels, this graph over here shows training and inference setups of some key transformer models using tensor slicing. With larger and future models requiring more slicing. We find that all reduce can be up to 36 to 46% of training and inference time, respectively. And in general, the proportion of all reduce increases as you slice a model more, and similarly, it holds for larger models which require more slicing. This overhead, however, can be addressed by taking advantage of the fact that both these compute and communication kernels actually execute in stages. For example, a GPU gem implementation usually tiles the output matrix and has work groups responsible to generate tiles. However, with large matrices, as well as limited compute units in GPUs, this execution happens in stages, and therefore the data generation also happens in multiple stages. Similarly, communication collectives also execute in multiple steps. For example, ring or reduce slices each of the partial arrays on each device and communicates only a chunk of the data at a time, requiring again multiple steps to complete the reduction. And these properties of both the compute and communication kernels lend well to their fine-grained interleaving. However, they are challenging to realize on a GPU. First, there is the software complexity. Fusing gems and collective operations can be difficult. Both gems and collective operations have dedicated kernel libraries, and especially for gems, these evolve with every new GPU generation. The second is, of course, interference. Both compute and collective kernels require compute units to execute and have memory accesses, which can result in interference and reduce the overall overlap efficacy. To overcome these, we propose T3. T3 enables transparent and efficient fine-grained interleaving. It does it by using a hardware track and trigger mechanism to track the producer gem's progress and automatically trigger communication when the data is ready. This avoids changing the producer gem kernel and allows for their independent evolution across generations. To reduce interference, T3 offloads communication to DMA engines and near-memory ALUs, maximizing the number of compute units that are available to the compute kernel, compute gems, and it reduces the amount of memory traffic overall. So let's look at T3 in action. Say, for example, we have 4 GPUs executing the respective gems and doing a reduce scatter, which is the first part of all reduce. In a steady state, each GPU is executing a gem stage. We use a pointer here. Each GPU is executing a gem stage and writing the output to their local memory. However, with T3, they're also communicating simultaneously. So, for example, GPU 0 here is communicating the data generated in the previous stage to the next GPU, thus overlapping both compute and communication. Simultaneously, it's also receiving a copy of the same data stage 3 from the other neighbor GPU, and with near memory computing, this results in the partially reduced version of the data in GPU 0's memory. And finally, as I mentioned, T3 uses a track and trigger mechanism. So a tracker at GPU 0 tracks all the updates, both local as well as the remote ones that are coming to memory, and triggers the communication of that partially reduced data when it's done. And again, this happens concurrently as the GPU executes the next stage data. To enable this, T3, of course, requires few system changes. Here, again, I'll show GPU 0. I'll show the system changes focusing on GPU 0, which I showed in the earlier slide. The first thing is that we require the gems updates or the output array to not be cached, so that all the updates, all the writes actually go to memory where they are reduced along with the DMA updates from remote. So DRAM basically acts as a point of synchronization for both the updates. In addition, we introduce a tracker at the memory controller, which also tracks the updates, both the local as well as DMA updates, and triggers the a pre-queue DMA command once it has received sufficient or all the required updates. Now let's look at each of these components in detail. As I mentioned, to transparently initiate communication, when gem data is ready, T3 uses a tracker, which tracks memory regions at a gem tile granularity. So as the gems and DMA updates arrive for a certain tile, they increment the counter at the corresponding table tracker entry. And once the number of updates sent to memory exceeds or reaches the expected updates, this triggers a DMA command, which is pre-queued in the DMA request table. Now, these structures are programmable for any collective type and implementation. As you can imagine, these things change. But they only require configuring just the gem output array. So they are mapped appropriately to the destination GPUs, along with the condition on which we want to trigger the DMA. Therefore, T3 avoids modifying the gem kernels. And further, it also, by using DMA engines, reduces the amount of compute units that's required by the communication kernels. To reduce the interference at memory, T3 first uses near memory computing. So for example, in baseline, when you're doing a reduce scatter, each GPU writes the partial value to the remote GPU's memory. The remote GPU then reads both its local copy as well as the one that it received to do the reduction, and then writes it to the next GPU. With near memory computing, the GPU only has to read the copy from its local memory and write it to the or update the remote memory location. And this reduces the amount of memory traffic that crosses the memory interface. In addition, T3 also modified the memory controller arbitration policy to prevent gem reads to be stalled because of DMAs. So basically, it prioritizes GEM's reads accesses and only issues DMA accesses once the DRAM queue occupancy is low. Overall, these two solutions reduce and manage the amount of traffic that communication introduces. With that, I'll briefly describe our evaluation and summarize the talk. To evaluate this, we used the GPU simulator Axel Sim, which we extended for multi-GPU simulations. We simulate 8 to 32 GPUs, each with a configuration shown on the table here, and an intra-node network bandwidth of about 150 gigabytes per second. In terms of applications, we studied gems and reduced scatters, the sliced gem and reduced scatter from a series of or a variety of transformers ranging from 8.3 billion to 540 billion parameters. And again, as I said, we are only simulating the gems and reduced scatter of these models. So to evaluate T3, we first find the maximum speedup that's possible with a fine-grained overlap. This is simply evaluated by checking the maximum of the gem and the reduced scatter runtime when they run in isolation. The graph here plots on the y-axis the speedup that we get from such overlap over the sequential execution on the GPU. And on the x-axis, it's plotting different transformer sublayers which are sliced in these models across multiple tensor slicing setups. This graph shows that with an ideal fine-grained overlap of these gems and reduced scatter can actually give us up to 50% of speed up over the baseline. And on average across all of these layers, it's giving us about 30%, 35% speed up. Comparing this with what we get with T3, we observe that speedups can go up to about 47%. And on an average, it's about 30% across these layers. And furthermore, this is only 5% away from the ideal speedups that I showed earlier. So with that, I'd like to summarize the talk. As models size increase and require distributed setups, the communication that's serialized can become a major bottleneck in their execution. Our work, T3, minimizes this impact of this communication by overlapping it with compute in a fine-grained manner. What's different from other works in T3 is that it does it efficiently by offloading the communication to DMA engines and using near memory computing, which helps reduce the interference with compute kernels, and further uses a hardware track and trigger mechanism to transparently orchestrate communication when data is ready. So this avoids complex kernel changes to interleave compute and communication. With that, I'd like to thank you all for attending, and I can take questions.
Thanks, Sujita. Any questions? Any questions from online?
Great talk. I'm Madan Muswati, Microsoft Research. So this mechanism seems to be general for overlapping two different kernels. Mm-hmm. So you could use this mechanism for overlapping two gems, for instance. Have we explored that? So what are the trade-offs?
I agree with you. Yes, it can be used. I think in terms of, yes, for example, in the tracker, for example, instead of tracking when the particular work group is complete, we are basically initiating communication. Instead of initiating communication, you would basically schedule a work group of the next gem kernel. I think the only challenge there is, I mean, here we are basically using a sort of contiguous memory space to transfer or initiate communication. For that kind of tracking, for example, basically the challenge is determining what work groups of, for example, a particular gem actually feeds into the next gem, right? And given there are so many different implementation of gem kernels, it can get hard. But if, for example, there are software hints provided by the user, I think that can be possible. And I agree, this can be extended in general for other kernels as well. Thank you for the great question.
Thank you.
Any other questions? Okay, let's thank the speaker. For the next talk, we have two speakers, Gerasimos Gerogiannis and Charles Bloch. They'll be presenting their work on two-phase.
All right. Hello, everyone. I am Gerasimos from UIUC, and today, together with my lab mate Charles, we're going to present our work titled Two-Phase, Combining Collective and One-Sided Communication for Efficient Distributed SPMM. Although all of the other papers in this session focused on how to optimize communication when both of the matrices involved are dense, or at least are being treated as being dense, in this work, we focus on SPMM, which is a multiplication between a sparse matrix and a dense matrix. It consists a major operation in graph neural networks and many linear algebra solvers. Large graph datasets today can reach terabyte scale. This makes distributed SPMM an extremely timely topic. In SPMM, a sparse matrix A is multiplied with a dense matrix B, with the result being another dense matrix C. The sparsity pattern of A, this means the locations of the non-zeros of A, determine the accesses to B and C. In particular, for every non-zero, its column will determine the row of B that will be accessed, and its row will determine the row of C that will be accessed. After the rows are accessed from memory, a SIMD operation occurs. This, in a shared memory setting, will lead to irregular memory accesses. However, in a distributed setting, which is the focus of our work, this triggers irregular communication. When we have distributed SPMM, the first thing we need to do is to decide how we will partition our matrices across all of the nodes in the system. In this work, we assume 1D partitioning, according to which each node will hold a consecutive set of rows from each of the matrices involved. It is important to note that with 1D partitioning, communication across nodes will happen only for the input dense matrix B, since the writes to the output matrix C are always local. As discussed, a non-zero will trigger a potentially remote access for B, and then will write the result locally to C. Depending on how the remote accesses for B are handled, we distinguish between two main communication patterns. The first pattern, which we call sparsity unaware, involves transfers of B, of the whole matrix B, to all the nodes. This can be typically achieved with synchronous collective transfers or collectives, which we will call sync transfers, and that were discussed in detail in the previous presentations. One example is that each node can broadcast its local partition of B to all of the other nodes, so that in the end, everybody gets everything. However, everybody gets everything is not good when we have sparsity, because it may lead to redundant transfers. Not everybody needs everything. An alternative to that is sparsity-aware transfers, according to which its non-zero will trigger an on-demand access to only the part of B to the specific row that is needed and is hosted in the remote node. This can be executed with asynchronous one-sided transfers, which we will refer to as async transfers. Unfortunately, this communication pattern does not come without its own drawbacks, since it may require many more network round trips. We're not using collective anymore, right? And in addition, the number of transfers of messages that need to be sent through the network increases a lot, and this increases also the software overhead. We profile the performance of the two different communication patterns for a set of 8 matrices from the popular sparse matrix collection, and we observe that for each matrix, the the communication pattern that performs the best depends on the specific matrix. In white, we can see instances where asynchronous performs better, and in red, we can see instances where synchronous performs better. This means that the optimal choice is matrix dependent, and this happens because the drawbacks of different methods are more significant for different matrices. However, non-zeros even in the same sparse matrix are not evenly distributed. Instead, they form denser and sparser regions. To this end, in this work, we claim that the optimal choice is not matrix dependent, but it is region dependent. In this work, to optimize communication, we utilize different communication patterns for different sparse matrix regions of the same matrix. How do we do that? Initially, the sparse matrix A contains a collection of non-zeros. Some of them are characterized as local input non-zeros. Those non-zeros will not trigger any remote transfers because the partition of B that they will access is already hosted locally. The rest of the non-zeros need to be classified as either synchronous or sync, or asynchronous or async. We classify non-zeros residing in denser regions of the sparse matrix as synchronous. For those non-zeros, the corresponding B row blocks are transferred with coarse-grained multicast operations. The remaining non-zeros are classified as async, and for those non-zeros, the corresponding B rows that need to be transferred will be transferred with fine-grained asynchronous transfers. We materialize this high-level idea into a concrete algorithm, which we call two-phase, and for which, at this point, Charles will give us more details.
Okay, hi. So now I'm going to talk about what two-phase looks like. Two-phase begins with a pre-processing step where we take a description of a sparse matrix and the characterization of the system that we're running on and determine exactly how we want to break this up into these sync and async communication primitives. Using this description from our preprocessor, we then implement a distributed SPMM algorithm that actually performs the operation that we're interested in. Our matrices are partitioned using 1D partitioning, like mentioned earlier, but we also further subpartition these into units that we call stripes. A sparse stripe is a collection of non-zeros, which just use the same communication flavor. And a dense stripe is the corresponding data in our dense matrix input that's actually going to be communicated using one of these two methods, according to how we classify our sparse stripes. The pre-processing step answers the question of whether we should use sync or async transfers for each of the stripes in our matrix. We begin the preprocessor with a computational model that is a simplified view of two-phase, where we assume that the sync and async portions are going to run completely in parallel. Under this assumption, we attempt to balance the amount of time spent in either of these two communication flavors, and we also try to use the best communication type for each stripe in our matrix. We do this by forming a simple linear cost model and using the cost estimates from this model to perform our partitioning. The cost model itself looks something like this. Here we model the cost of communication for our asynchronous stripes as a function of the number of dense columns, as the number of columns in our dense input matrix, the number of rows of that matrix that we need to transfer, and the number of async stripes in total in our system. Clearly, these parameters depend on our matrix inputs and the decisions that we take during our pre-processing classification step. But we also have other scaling factors that depend on system characteristics like bandwidth, latency, or software overheads. We determine these second set of parameters at installation time by running a system characterization step and linear regression. After our pre-processing step is complete, we have a matrix where we've classified our non-zeros into those that already have their data local and so don't need communication, those that are going to use sync communication, and those that are going to use async communication. We split this up farther into two substructures, one that contains all of the local input non-zeros and the sync non-zeros, and one that contains all of the async non-zeros. This is just for ease of handling in the algorithm, but we also store these in different formats. Both are COO with some additional metadata about the communication and tiling, but we store the sync structure as a row major format to optimize for local computational performance. And we store the async structure using a column major format so that we can easily iterate over the columns and reduce the complexity of communication for that one. Two-phase itself is a parallel algorithm where some threads begin their execution by issuing a whole bunch of collectives for the sync communication. And then once these collectives complete, perform a local computation on the received data, where simultaneously other threads issue in sequence fetch requests to local nodes, followed by local accumulation, followed by more fetch requests. And by performing this with several threads, we can overlap local communication and computation. Once both of these halves complete, we've completed our SPMM operation. We evaluate two-phase on the NCSA Delta supercomputer at Illinois, which is a supercomputer where each CPU node contains 128 CPU cores and 256 gigabytes of RAM. And we evaluate a scaling performance from 1 to 64 nodes. We use OpenMPI for programming internode communication and OpenMP for local multi-threading. And we compare against a handful of both sparsely unaware and sparsity aware baselines. We use matrices from SweetSparse, containing up to 3.6 billion non-zeros and 214 million rows, and scale our dense matrix inputs from 32 to 512 columns. So just for reference, 214 million rows and 512 columns is terabyte scale data that we're talking about here. Looking at the performance of two-phase, we see a reasonable speed up over our baselines of about 2.11x compared to the best choice parameterization of one of our sparsely unaware baselines for 128 dense columns on 32 nodes, and an average of 1.99x on 32 nodes, with generally better performance as the size of the problem scales. We also perform a strong scaling analysis. I'm just showing two matrices here, but we see that two-phase scales as well or better than our baselines in general. So in conclusion, SPMM is an important communication-bound workload in a lot of today's applications, and existing communication methods aren't exactly optimal because sparse matrices often contain sparser and denser regions. And by paying attention to this variation internally, we can schedule communication differently according to those characteristics and improve performance. We implement these ideas in two-phase, which combines collectives and one-sided communication to achieve about a 2x speed up and better scalability over a bunch of state-of-the-art algorithms. So we're happy to take any questions.
Thanks, Derasimus and Charles. Any questions?
Right. So I wonder whether you have observed the load imbalance when you when you decide the partition and the policy.
Yeah, so we definitely observed load imbalance for some matrices because sparse matrices are so varied. You know, for some matrices it's not a problem, for others it is. 1D partitioning without reordering does see load imbalance on some. This wasn't the main concern of our work, but yeah.
Right. And another thing is that it is based on the fact that you know the matrices, right? So what happens if you chain a number of operations and you have the result and you want to perform the computation on that? So it is
right. So our two-phase mainly targets matrices that are known in advance. You can think of it like an extra preprocessing cost for matrices that are going to be used multiple times, such as graph neural network inference. And you can think of it as a preprocessing cost, which is equivalent to quantizing neural networks to have them quantized for inference. So it's, you know, something.
Okay. Thank you.
Any other questions? Anything online? Okay, I have a question. Are you considering memory usage when you decide between sync versus async? You know, when you choose sync, are you broadcasting? Are you doing a ring style thing to handle memory usage? So how is that part of your decision making?
Yeah, so when we're doing sync transfers in our implementation, we use broadcast. We considered using the ring step in. The issue with there is it's hard to do ring transfers when you're only transferring a small subset of your dense matrix, because then you're still piping everything through everything. As for size, yeah, on a few of our matrices, that becomes an issue, especially as the size of the dense matrix scales. And in those cases, we have some slight optimizations to our pre-processing step that more heavily weight the asynchronous communication, since that has to keep data around for less time and can reuse buffers a bit more efficiently.
Okay, thank you. Okay, let's thank the speakers. Thanks, everyone. Thanks for attending the session.